In this video, we are going to cover the concept of work and apply integral calculus to solve problems. To start, first we need to have some definition of work. Work can be defined to be equal to a force times a distance. If I'm pulling a wagon, I am applying a force in pulling it, and if there's a displacement along the x-axis, I'm doing work. The unit of force is the Newton, distance in meters, the unit of work is the joule. Now, this equation assumes that force is constant, but in fact force may vary as a function of x, in which case we need to sum up each contribution. Now, of course, this is really only approximate and becomes more accurate the greater n is. We also recognize that this is a Riemann sum, so if we apply the limit, this becomes a definite integral. Okay, now that we know that work can be written as a definite integral, we are now prepared to deal with more challenging problems. For a simple example, Hooke's law says that the force to pull on a spring is equal to some spring constant times the displacement. What is the work done on a spring stretching it from 0 to 0.1 meters with a spring constant of 40 newtons per meter? Well, all we have to do is put the function in the integral, integrate,
Okay, let's try this problem. A spherical tank of radius r is equal to 4 meters is full of water. Find the amount of work required to pump out all the water out of a spout 1 meter above the tank. First, let's draw a diagram. Here we have a tank at 1 meter above is a spout. It has a radius of 4 meters. What we will do is look at some slice within the tank, like that, with thickness delta y and radius r. We want to know what the work would be to move this slice out of the tank. Well, it's going to be approximately equal to the force times the displacement. Well, F is going to be equal to mg, but M is going to vary because not every slice is going to have the same mass because they'll have a different radius. So we need to work out what the mass is. Well, we know that mass is equal to the density times volume. And volume is equal to the area times the thickness of the thin disk. And the area is going to be pi r squared. And multiply that by the thickness gives us the volume. So what we now want is a relationship between r and y. We want to go from r to y. If we looked at a cross-section of a tank, our slice might exist here, and in which case r is there. And we can write the radius being here as being 4, and if we put our origin here, then our height is here. In which case we can see that 4 squared is equal to y squared plus r squared, or r squared is equal to 4 squared minus y squared. So that tells us the relationship of r. We can put that into the volume equation. Which means that the force is going to be rho g pi 16 minus y squared delta y. Next, we need to know the distance. Well, back to our diagram here. The top of the spout is going to exist up here, which is at the point 0, 5. Because the radius of the sphere is 4 and the spout is 1 meter above that, so it's going to be 5 meters from the origin. So that means that the distance the disk has to then travel is going to be 5 minus y. If y is 5, it means we're at the top of the spout, then the distance is 0. If y is minus 4, then the distance is 9. We have to travel the entire tank, the diameter of the tank upward, which is 4, and then one more to the spout, which gives us 9. Which means the work done is approximately equal to rho g pi 16 minus y squared 5 minus y delta y for some slice. And the total work is approximately equal to the sum. Now the disk is only approximate, but the thinner the disk, the more accurate the approximation gets. So if we then apply the limit, we get a definite integral and we use the bounds minus 4 to 4 because of the tank. And then all we have to do to find the work done is to then integrate Once we're at this step, all we need to do is then plug in our values and we would get our answer. I will provide the answer in the description below.
Thank you for watching my video, and if you enjoyed it, feel free to give it a like and subscribe for more content.